Euclid, the father of geometry, began with 5 postulates. A postulate is a statement that's assumed to be true. It's not proven like a theorem. A theorem you prove, a postulate you assume to be true. He started with 5 postulates, and from there he derived all the other theorems of geometry. And the book that comprised all this information was called The Elements. The Elements, one of the most important mathematical works in all of human history, and Euclid, of course, is one of the most important mathematicians in all of human history. So let's take a look at his 5 postulates. These are the starting points, and everything else, angle side angle, the Pythagorean theorem, everything else he proved from these 5 things. Here are the postulates. A straight line segment can be drawn joining any 2 points. Any straight line segment can be extended indefinitely in a straight line. Remember, a line segment has 2 endpoints. A line goes on infinitely. Given any straight line segment, a circle can be drawn having the segment as a radius and 1 endpoint as the center. All right angles are congruent. And here's the weird one. If 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side if extended far enough. That's a weird one, right? And Euclid did his best to stick with just the first 4. He and then many other people tried to prove the 5th postulate based on the first 4, and no one could do it. And it really reveals a very important aspect of geometry, as we're about to see. Some mathematicians decided to negate the 5th postulate, to just use a different postulate as the 5th postulate. And they ended up with a different geometry, the theorems are all different, the way that all the pieces fit together, those are totally different because you change this thing. And that's where you get the spherical, the elliptical, and the hyperbolic geometries. One of the people who did this experiment to show that if you change this postulate, you can get a totally different system of geometry, but one that works. It is internally consistent. It works. It's logical. It was the great mathematician Gauss. Now, Gauss recognized that something like this would be so controversial that he figured it out and he just didn't publish it. He didn't show it to anybody else. So even though he was either one of the first or arguably the first person to come up with these non-Euclidean geometries, he wasn't the first person to publish that by any means. Now, non-Euclidean geometries, interestingly enough, they do have some physical applications, especially in some very, very advanced physics. Here's a quote from Paul Dirac. Non-Euclidean geometry and non-commutative algebra, which those of you guys who study algebra in college, real abstract algebra, not the high school algebra, which were at one time considered to be purely fictions in the mind and pastimes for logical thinkers, have now been found to be very necessary for the description of the general facts of the physical world. And he's right. When it comes to things like the theory of relativity and all that, non-Euclidean geometries actually have a very, very direct application. But that, to me, is not what makes them great. To me, it is the fact that they are fictions of the mind and pastime for logical thinkers. That by itself is good. A lot of times when we're developing our physical bodies, we'll do things that might not have a direct application. You bench press, push-ups, pull-ups, but doing them makes our bodies better, stronger, superior. And with the mind, even doing things that are totally made up, like playing chess, it's a game, the rules are made up, doing that develops and builds the mind. And these mathematical exercises can also develop and build the mind. Now, do they have direct application? Yes, of course. Number theory is used in things like Bitcoin and other cryptocurrencies to allow people to carry on secret transactions without any government oversight. So it's not that there is no application, but to me, the most important application of this is the fact that it develops your logical reasoning ability, your spatial reasoning ability, your creative thinking. It makes you smarter, and that to me is what really makes this worthwhile. Anyway, for those of you who want to learn more about non-Euclidean geometries, that is currently outside the scope of our method, but if you study mathematics in college, you will certainly have the opportunity to do that. And even if you decide that you don't want to spend your time studying that in college or don't want to go to college at all, there are so many great online resources that will let you really study and explore this fascinating branch of mathematics.